Welcome to Talk Tensors, the podcast exploring the bleeding edge of machine learning, where we separate the signal from the noise in the AI landscape.
And we try not to get lost in the hype.
I'm your host, and as always, I am here to dig through the RCIV stack so you don't have to.
And I'm joining you to make sure we actually understand the math behind that hype. And today we are dissecting a technology that claims to solve one of the biggest, most persistent headaches in modern large language model training.
That is no exaggeration at all. We are looking at a paper that has been, just completely dominating the discourse lately.
Oh, absolutely.
If you've been on X or, any of the ML subreddits, you have seen this acronym. It promises to take the current king of alignment, the technique that made ChatGPT and Claude and Llama what they are today, and essentially tell it to take a long vacation.
It's a pretty bold claim. The paper is titled Direct Preference Optimization. Your language model is secretly a reward model. And honestly, the title alone is a huge spoiler for the mathematical magic trick inside.
I love that title. Your language model is secretly a reward model. It sounds like a conspiracy theory you'd find in some deep corner of the internet.
Right, but it's actually a theorem. It's grounded in some really elegant math.
Okay, but before we get to the solution, we have to talk about the problem. We really need to set the scene regarding the current king of the hill, reinforcement learning from human feedback, RLHF.
Right, RLHF. This is, for all intents and purposes, the secret sauce. If you take a raw language model 1 that has just been pre-trained on, a giant chunk of the internet, it's basically a chaos engine.
It's a brilliant chaos engine, but it's still chaos.
Exactly. It just wants to predict the next word. It doesn't know if it should be helpful or toxic or just start spitting out gibberish. RLHF is the process we use to tame that beast.
It's the finishing school for LLMs. You send your wild internet brain to a Swiss boarding school, and it comes back polite and helpful.
That's a great way to put it. But the problem is, this finishing school is... it's notoriously difficult to get into and even harder to run. It's complex, it can be incredibly unstable, and it is computationally eye-wateringly expensive.
You're not kidding.
It involves training a whole separate model, a reward model, and then using a really complex reinforcement learning algorithm, usually it's PPO, proximal policy optimization, to fine-tune the main model.
And anyone in our audience who has actually tried to train a model using PPO is probably nodding along right now, maybe even wincing a little.
They're having flashbacks.
Total flashback. It is such a delicate balancing act. You have to load multiple giant models into memory. The training loop is painfully slow. And if you get the hyperparameters, the settings just slightly wrong, the model doesn't just learn poorly, it completely collapses.
It just outputs nonsense. It unlearns how to speak. It's the ultimate bottleneck. You have this beautiful, powerful, pre-trained model, but to make it safe and useful for a chatbot, you have to drag it through this messy, unstable, and frankly, terrifying reinforcement learning pipeline.
It's affected. The results speak for themselves, but boy, is it inefficient.
Incredibly.
So enter the challenger. Today's deep dive is dedicated to direct preference optimization, or DPO.
DPO.
The core thesis here is, on the surface, startlingly simple. DPO promises to skip all the complex, scary parts of RLHF.
The whole reward modeling and RL loop, yeah.
It optimizes the language model to align with human preferences directly without needing that explicit reward model or a reinforcement learning loop at all.
And I really want to emphasize the technical gravity here. This isn't just a clever heuristic or, a shortcut. It's a full-on mathematical reparameterization. The authors derive a way to turn this horribly complex RL problem into a simple classification problem.
A classification problem?
Yes, specifically a binary cross-entropy loss. It's the same kind of math you'd use to classify an image as a cat or a dog.
So instead of this complex optimization loop where the model is guessing and getting a score and guessing again, it's just looking at two answers and basically learning this one is better than that one.
Precisely. That's it. And why this matters so much right now is all about scale and accessibility. If this holds up, and all the evidence in the paper suggests it does, the barrier to entry for aligning these super smart models just drops through the floor.
It's not just for the giant labs anymore.
Not at all. It removes the need for the massive compute infrastructure you need for PPO sampling. You don't need a whole fleet of A100s just to hold all the different models in memory anymore.
That is a massive shift. It sounds almost too good to be true. Getting the same or even better performance with a fraction of the complexity and cost.
It does, which is why we need to dig in.
Okay, let's do it. Let's unpack this. I really want to understand exactly how this works, but to do that, we first need to get a clear picture of what it's replacing. So walk us through the status quo. What does that standard 3-step RLHF pipeline actually look like in detail?
Sure. So the standard pipeline, the one that OpenAI really popularized and now pretty much everyone uses, has 3 very distinct steps.
Okay, step 1.
Step 1 is SFT, supervised fine-tuning.
This is the instruction tuning phase we mentioned earlier, right?
Correct. You take your raw base model and you feed it a curated data set of high-quality examples. You show it thousands of prompts and ideal responses. Things like, write me a short story about a brave toaster. And then you show it a great short story about a brave toaster.
So you're just teaching the model the format of a conversation. You're showing it how to be a helpful assistant, how to follow instructions.
Exactly. It gets the model to mimic the style of a good chatbot, but it doesn't necessarily understand the underlying principles of what makes one answer better than another in a more nuanced way. It just knows what a good answer looks like.
It's learned the script, but it can't improvise yet. Doesn't have taste.
Perfect analogy. It has no taste. Okay, so that's step 1. Step 2 is where we try to teach it taste. This is reward modeling.
Okay, and this is where the humans come in.
This is where the humans come in. We collect human preferences. We give the SFT model a prompt, say, explain quantum physics to a 5-year-old. Then we have it generate 2 different answers. We'll call them answer A and answer B.
The classic A/B test.
Right. Then a human labeler, a real person, looks at both of them and says, you know what, answer A is clearer or answer B is more creative. They just pick a winner.
And you do this thousands or tens of thousands of times.
Or hundreds of thousands of times. And you take all of these comparisons, this giant data set of prompt, winner, loser, and you use it to train a completely separate neural network. This is the reward model.
The critic.
The critic, exactly. The reward model's only job is to learn to predict which answer a human would prefer. It looks at a model's output and spits out a single number, a scalar score. A higher number means a human would probably like this. A lower number means a human probably wouldn't.
So now we have a model that can grade the test. We have an automated human taste predictor.
Precisely. And that leads us to the final, most painful step, step 3, RL fine-tuning, almost always with PPO.
This is the friction point, the nightmare stage.
This is where it all gets messy. So you take your original language model, we call it the actor, and you let it generate some text. Then you take your new reward model, the critic, and you have it grade that text. It gives it a score.
And based on that score?
Based on that score, you use the PPO algorithm to update the actor's weights, trying to nudge it in a direction that will get it higher scores in the future.
And this is where the whole thing can just explode.
It really can. Because first, to get that score, you have to sample a full generation from the model during the training loop. That is incredibly slow. It's not like a simple forward pass.
Right, it has to write out the whole answer token by token.
Yes. And then you have this other problem. If you just tell the model, maximize this reward score, it will find the weirdest, most bizarre ways to do it. It'll find loopholes in your reward model. We call this reward hacking.
Like it might just start outputting the word excellent over and over again.
Right.
Because it learned that word gets a high score.
Exactly. So to prevent that, you have to add a constraint. You have to say, okay, maximize the reward, but don't drift too far from how you originally talked. This is the KL divergence constraint. It keeps the model grounded.
So you're juggling all these pieces.
They're juggling the actor model, the reference model, which is a copy of the original SFT model for the KL check, the reward model to provide the score, and often a fourth model, the value function model, which helps stabilize PPO.
That is a lot of VRAM. That's a huge amount of graphics card memory.
It's a massive amount. And on top of all that, PPO is just so sensitive to its settings, its hyperparameters. If your learning rate is a tiny bit too high or your batch size is off, the model doesn't just learn slowly. It can completely destabilize and forget everything. It produces gibberish.
So we've built this incredibly complex, fragile, expensive Rube Goldberg machine of reinforcement learning just to get the model to be polite and helpful.
That's the state of the art.
And DPO comes along and says, you know what, we don't need the machine.
DPO just cuts the Gordian knot. It says the machine is the problem.
What is the magic trick here? How can you get rid of all that complexity and still get the same result?
The magic trick is in the math. It's a really profound insight. The researchers realized that there is a direct analytical mapping between a reward function and the optimal policy it produces.
Okay, let's slow down and really unpack that. Analytical mapping.
Yeah.
What does that mean in plain English for those of us who aren't mathematicians?
Okay, so in the standard RLHF setup, We assume there's some hidden, invisible reward function out there that perfectly represents what humans want.
The ideal taste function.
The ideal taste function, yes. We try to approximate that function by training our reward model neural network. Then we train a policy, our language model, to get high scores from that reward model. So it's two separate steps. Learn the reward, then optimize for the reward.
Right.
The breakthrough in this paper is the realization that you can mathematically flip this relationship on its head.
You can invert it.
You can invert it. They derived a formula where you can express the reward function directly in terms of the optimal policy.
Wait, so instead of saying, here is a reward model, now go figure out how to please it, you're saying something like, if we already knew the perfect, final, aligned model, we could just look at it and instantly know what reward function it was optimizing for.
That is exactly it. And because of this direct mapping, you can do something really clever. You can take the loss function that you would normally use to train the reward model, which is just a simple binary classification loss on that preference data, remember?
Winner versus loser.
Winner versus loser. And you can rewrite that equation. Everywhere you see a term for the reward model, you can just substitute it with a term that involves the language model policy itself.
Your language model is secretly a reward model. It's not just a catchy title.
It's the literal punchline of the derivation. That's the aha moment. Instead of training a whole separate model to figure out what is good, you define the preference loss directly in terms of the policy itself. You are optimizing the policy to satisfy the preferences directly in one step.
That's brilliant. Let me try an analogy here to see if I've got this. The old way, RLHF, is like an actor trying to learn a role for a film.
Okay.
They perform a scene, then a critic, a separate person, the reward model comes over and gives them a score out of 10. That was a 7. Try it again. That was a 4. You need more emotion. The actor has to guess and experiment to figure out how to improve their score. It's this whole feedback loop.
That's a very good representation of the PPO loop, yes. The actor and critic.
And DPO then is like cutting out the critic entirely. Instead of hiring a critic, the actor just watches 2 different takes of their own performance. Take A got a huge round of applause from the audience, and take B got total silence. The actor just looks at the 2 and says, okay, I need to do more of whatever I did in take A and less of whatever I did in take B.
That's it. That's a perfect analogy. The actor learns directly from the preference data, the applause. They don't need a critic to translate applause into a score. They just optimize for the applause directly.
The preference is the signal. You don't need to model the preference first.
You don't. The policy network itself ends up representing both the language model and the implicit reward. The DPO update, mathematically, just increases the relative log probability of the preferred response compared to the dispreferred one.
So it's looking at the winner and the loser, and it's just nudging the model's weights to say, make the winner more likely, make the loser less likely.
Yes, but, and this is a crucial nuance that makes DPO so stable, it's not just a simple maximize winner, minimize loser. The update is weighted.
Weighted? Weighted by what?
It's weighted by how wrong the model's implicit reward currently is. So the algorithm looks at the probability ratio between the winner and loser. If the model effectively already knows that the winner is better, if it already assigns a much, much higher probability to the winner than the loser, the update is very small. The gradient is close to 0.
It doesn't waste time and energy fixing what isn't broken.
Exactly. But on the other hand, if the model ranks the loser higher than the winner, if it's confident and completely wrong, the update is very aggressive. It applies a much stronger gradient to correct that big mistake. This dynamic weighting is naturally derived from the math. It's not something they just added on. And it's what keeps the training so stable.
That's really clever. It focuses its attention on the biggest errors. Now, what about the other big problem from RLHF? The model drifting off into la-la land. You mentioned the KL divergence constraint, which stops the model from forgetting how to speak English while it's chasing rewards. Does DPO have an equivalent to that?
It does, but again, it's just built in. This is the elegance of the solution. The DPO formulation naturally includes the reference model, that's the original SFT model, as an anchor.
So it's always comparing to where it started.
It is. The update function is mathematically structured to maximize the implicit reward while simultaneously minimizing the KL divergence from that reference model. But instead of being this clunky, explicit penalty term that you add to a complex RL objective, it's just part of the single classification loss equation.
So it's doing the exact same job as PPO's KL constraint optimizing preferences while staying grounded. But it's doing it with one clean, simple equation instead of a whole separate mechanism.
Cleaner and so much more computationally light. Which brings us to the mechanics of the training process itself. You asked before if this is still reinforcement learning. The answer is a definitive no. It is supervised learning.
And that's the key distinction, isn't it? We are back in the comfortable, well-understood world of supervised learning.
We are. No more sampling loops. In PPO, for every single training step, you have to generate text from the model, which means running it autoregressively, token by token. That is so slow.
Painfully slow.
With DPO, you just take your data set of prompt, winner, loser. You run them all through the model in a big batch to get their probabilities, and then you calculate the loss.
It's just a forward pass and a backward pass. Standard stuff.
Standard back propagation. This yields a massive speed up. And think about the memory savings we touched on. With PPO, you need the policy model, the reference model, the reward model, and the value model all loaded up. With DPO, you just need the policy model you're training and the reference model. And you can often freeze the reference model or handle it in a more efficient way.
You've essentially cut the VRAM requirement in half, maybe even more.
At least in half, which is why I mentioned democratization earlier. This means you can potentially run DPO fine-tuning on hardware that would just completely choke on PPO.
Okay, so the theory is beautiful. The math is undeniably elegant. But as we both know, especially in machine learning, elegant math doesn't always translate to better models. Sometimes the messy brute force method just works better in practice. So the big question, does it actually work? Or is this just a really pretty paper?
That's the million-dollar question, and thankfully the paper is very thorough on this. They ran experiments across 3 completely distinct domains: sentiment generation, summarization, and dialogue. And in pretty much every single case, DPO either matched or more often beat PPO.
Okay, let's go through them. Let's start with sentiment generation. This was using the IMDb data set, right? Movie reviews.
Yes. The task was simple and very controlled. You take the beginning of a movie review, and the model has to generate a continuation that has a positive sentiment. It's a good controlled experiment because you can easily and automatically measure positive sentiment with another classifier.
So you have a clear, objective score, and what did they find?
They looked at what's called the efficient frontier. Basically, for any given amount of deviation from the base model, that KL divergence we talked about, how much reward or positive sentiment can you get? And DPO achieved the best frontier.
Meaning what exactly?
Meaning, for the same amount of change to the model's core personality, DPO was able to get higher positive sentiment scores than PPO was. It's more efficient at learning the task without breaking the underlying model.
So it's more efficient at extracting the desired behavior per unit of change. That's a great result for a controlled task.
It is. But you're right, that's a toy task. The real test is something much more complex, like summarization.
The Reddit TLDR dataset. This is a classic RLHF benchmark.
A very famous one. The task is to take a long, often rambling Reddit post and write a short, concise, too long, didn't read summary. This is much harder to score objectively.
So how do they measure success here?
They measured win rates. They would show a Reddit post to a model trained with DPO, one trained with PPO, and they also had the original human written summary. Then they'd ask an evaluator, in this case another powerful AI model, which summary was the best.
And the results?
DPO achieved a 61% win rate against the human written summary.
Well, wait, 61% against the human writers?
Yeah.
So it was preferred over the human summary more often than not?
Yes. Now compare that to PPO, which in their experiments achieved about 57%. Now that 4% gap between 57% and 61% might not sound like a huge number, but in these large-scale LLM benchmarks, a 4-point gap in win rate is very significant.
That's a solid win. But you said there was something more interesting here.
Yes, the robustness. This, for me, was one of the most compelling results in the whole paper. It's about temperature.
Okay, explain temperature for our listeners.
Temperature is a setting you use during generation that controls the randomness or creativity of the model's output. A low temperature makes the output very deterministic and predictable. A high temperature makes it more creative, more random, more willing to take risks.
And what happened when they changed the temperature?
The researchers found that the PPO trained model was incredibly brittle. Its performance was good at the specific temperature it was trained at, but if you increase the temperature to make it more creative, its quality just fell off a cliff. It started making much worse summaries.
It's a one-trick pony.
Yeah.
It only works well under the exact conditions it was trained for.
A very brittle one-trick pony, yes. DPO, on the other hand, was robust and stable across a whole range of temperatures. Whether you wanted a straightforward deterministic summary or a more creative one, DPO maintained its high win rate.
That is huge for real-world deployment. You don't want a model that falls apart just because a user slides the creativity toggle up a little bit.
It's a massive practical advantage. Okay, so what about the third task? Dialogue.
Right. This was the Anthropic helpful and harmless dataset.
Yes. This is a much harder, more open-ended task than sentiment or even summarization. It's single-turn dialogue, answering user queries with the goal of being, well, helpful and harmless.
A lot more nuance there.
A ton more. And the result here was probably the most stark in the whole paper. DPO was the only method they tested that significantly improved over the baseline.
What was a baseline?
The baseline was just picking the preferred response from the original human-labeled dataset. So basically the best you could do without any new training. DPO cleared that bar easily. PPO, however, actually struggled to beat the baseline in this specific setup.
Wait, you're saying the multi-million-dollar super complex PPO pipeline couldn't even beat just picking the better of two pre-written answers?
In this specific configuration, yes, PPO had a very hard time. And this really highlights how ridiculously difficult PPO is to tune. The authors note that DPO converged to its best performance relatively quickly and reliably. PPO is this dark art of tweaking dozens of little hyperparameters just to get it to learn anything at all without completely collapsing.
That speaks volumes. It's not just about the peak performance you can theoretically achieve. It's about the reliability of actually getting there without tearing your hair out.
Exactly. And there is one more result that I think is absolutely critical: generalization.
Right, because fine-tuning on one specific type of data is great, but does it break the model for everything else? Does it overfit?
The classic overfitting problem. So they tested this on what's called out-of-distribution data. They trained all their summarization models on Reddit posts, which have a very specific informal style. Then they asked those same models to summarize news articles from the CNN Daily Mail dataset.
A completely different style of writing, much more formal, structured.
Completely different domain. And the DPO trained policies generalized much better than the PPO policies to this new type of text. Even though they were only ever trained on rambling forum posts, they could handle summarizing structured news articles more effectively.
That suggests that DPO isn't just memorizing the patterns in the preference data, it's actually learning a more fundamental, robust understanding of what constitutes a good summary.
That's the holy grail, isn't it? We want models that learn principles, not just mimic patterns.
Precisely.
And one quick note on the evaluation methodology, because I know our listeners are rightly skeptical of automated metrics.
Using AI to grade AI.
It's become the standard, for better or worse. But they did their homework here. They ran a study to validate it. The DPO results showed that the judgments made by their evaluator model, GPT-4, correlated very strongly with judgments made by humans.
How strongly?
To the point where GPT-4 agreed with a human evaluator as often as two different human evaluators agreed with each other.
Okay, so it's about as reliable as another human. That's a reassuring sanity check. So let's pull back and look at the big picture here. What does all of this mean for the field? What does this mean for the average Joe machine learning engineer working at a startup or in a smaller lab?
It means the average Joe might actually be able to properly align their own models now.
It's not gate-kept by the giants with massive compute budgets anymore.
That barrier is lowered significantly. You no longer need a dedicated, specialized RL engineering team just to get your alignment pipeline to not explode. You don't need a massive cluster of GPUs just to hold the PPO state in memory.
It democratizes alignment.
It really does. And it brings stability. It removes all the dark arts and the black magic of tuning PPO hyperparameters. If you have a preference data set, a simple CSV file that says, for this prompt, this answer is better than that answer, you can just run DPO as a standard supervised training job. It's much more predictable.
Now, what about the scale of the models themselves?
Well, it makes it feasible to fine-tune much larger models on consumer or, prosumer grade hardware, because you don't need to load the policy, reference, reward, and value models all at the same time. You can fit a much bigger model into the same memory footprint.
So we might see a Cambrian explosion of finely tuned, highly aligned models coming from the open source community simply because the tooling just got 10 times easier and cheaper.
I think that is a very, very safe prediction to make. We're probably already seeing it.
However, this is talk tensors, and we don't just drink the Kool-Aid. We have to be critical. We have to look at the limitations. DPO can't be perfect. Nothing ever is.
No, it's not a silver bullet, and the authors are very honest about this. There are a few points of academic skepticism worth noting. First, there's a subtle theoretical point about something called equivalence classes.
Equivalence classes. Okay, that sounds like abstract algebra. Break it down for me.
It is a little. So technically, the preference models that this whole theory is built on, models like Plackett-Luce and Bradley-Terry, have what are called equivalence classes of reward functions.
Meaning?
Meaning that for a given set of preferences, there could actually be multiple different reward functions that perfectly explain those preferences. DPO, for mathematical convenience, selects a specific one from that class. It assumes a certain structure to the reward function to make the math work out so cleanly.
So it's making a simplifying assumption that might not always be perfectly true in the messy real world of human preferences.
Potentially. It's a mathematical constraint that seems to work incredibly well in practice, but it is an assumption.
Okay, what's next on the list of caveats?
The age-old risk of over-optimization. We sometimes call this Goodhart's law.
When a measure becomes a target, it ceases to be a good measure.
The very same. The model starts gaming the metric. Even with DPO, which is more robust, they saw in some of their experiments that the win rates would start to dip slightly after too much training.
So it starts to find weird edge cases to win the preference game.
Exactly. The model starts to exploit the specific quirks and biases of your preference data set rather than learning the general principle of what you want. It's like it's memorizing the answers to the test instead of learning the subject.
So you still need to be careful. You still need to watch the training graphs and know when to stop before it goes off the rails.
You absolutely do. DPO seems to be much less susceptible to this catastrophic failure mode than PPO, but it's not completely immune. And finally, the biggest limitation of all, and this is the one DPO doesn't solve, data hunger.
The garbage in, garbage out problem.
The fundamental problem. DPO brilliantly solves the training bottleneck. It makes the algorithm simple and efficient, but it does absolutely nothing to solve the data collection bottleneck.
It still needs high-quality food to eat.
Exactly. It still relies on thousands and thousands of high-quality preference pairs. You need a data set where output A is legitimately thoughtfully better than output B. If your preference data is noisy or biased or just plain wrong, DPO will very efficiently and very stably learn to be noisy, biased, and wrong.
It's an incredibly efficient optimizer, not a magician. It just optimizes whatever you give it.
Precisely. It doesn't create high-quality human judgment out of thin air. That's still the hardest part.
Okay, that is a fantastic, thorough breakdown of the paper. We've gone from the multi-headed hydra of RLHF to the, well, mathematical elegance of DPO. We've looked at the theory, the practical results, and the important limitations.
A good tour.
Now, it is time for my absolute favorite part of the show.
Oh, no. I know what's coming.
Oh, yes. It is time for Novel Notions.
You have the disclaimer ready, I hope.
I have it memorized. Standard disclaimer. The following concepts are for entertainment purposes only and represent outlandish, highly speculative extrapolations of the technology discussed. Please do not build your next billion-dollar startup based on these ideas without doing the math yourself.
All right, proceed with caution.
Okay. Idea number 1. I'm calling this the personality swap interface.
Personality swap. Okay, I'm listening.
So the entire premise of DPO is that your language model is secretly a reward model. Right? The model's preferences are baked directly into its weight.
Correct. The policy is the preference.
So imagine we have a base model, and we've fine-tuned it with DPO on a few different high-quality preference data sets. One data set strongly prefers polite and formal responses. Another one prefers sarcastic and witty. And the third one prefers, pirate speak.
Okay. A very specific use case, but go on.
Instead of having 3 separate, giant, multi-billion parameter models stored on a server, what if we just maintained a library of lightweight difference vectors? Just the changes that the DPO updates made to the base model. Since the reward is implicit in those weights, could we theoretically hot swap personalities, the implicit rewards, instantly at inference time?
You mean without reloading a whole new model?
Mathematically? That's intriguing. If you can view the DPO update as a specific shift in the model's implicit reward function, and you could isolate those weight shifts, you could, in theory, add or subtract them from the base model. Exactly. A user could literally have a slider on their interface. Sarcasm level, 10. Formality, 8. And under the hood, the model is just doing some simple vector arithmetic. It's mathematically reweighting its own implicit reward function in real time, adjusting the log probabilities of the next token to favor outcomes that align with that new hybrid personality.
You're talking about doing arithmetic in the weight space of the implicit reward. We already know that task vectors are a thing in other areas of LLM research where you can add or subtract skills. Since DPO proves the policy is the preference, manipulating the weights is directly manipulating the preference. You might not even need to retrain. You could potentially just interpolate between a helpful DPO model and a sarcastic DPO model to get a helpfully sarcastic hybrid on the fly.
Alignment on demand. No more year-long arguments about what a single model's one true personality should be. You just let the user tune the implicit reward function to their liking.
It's a fascinating idea. It treats alignment not as a static, baked-in constraint, but as a dynamic user interface feature. I like it.
All right. Idea number 2. This was a little more ambitious. I call this recursive self-DPO, or my preferred title, the singularity spin.
I knew we'd get to the singularity eventually. It's inevitable.
We have to. The big problem with trying to make self-improving AI with PPO was that PPO is unstable. You couldn't just let it run on its own feedback forever because the noise would compound and it would eventually collapse into gibberish.
True. It's too chaotic for a stable recursive loop.
But DPO is stable, and it's computationally cheap.
Okay, I see where you're going with this.
So imagine a loop. An LLM generates 2 different answers to a complex question it poses to itself. Then a smaller, highly specialized critic model, or even the main model itself using a chain of thought process, analyzes both answers and picks a winner. Answer A was more logically consistent. Answer B used a flawed premise.
It's generating its own synthetic preference data.
Exactly. Then, because DPO is so cheap and stable, the model runs a DPO update on its own weights. Maybe it does this overnight while it's idle. It uses its own logical conclusions from the day as the training data for the next day.
It's a form of online learning, but for alignment. It wakes up every morning slightly better aligned to its own best, most consistent logic.
It's continually refining itself, not based on slow, expensive human feedback, but based on its own internal consistency.
The why here is really compelling. As you said, PPO was too noisy for this kind of continuous self-improvement. The noise would compound and destroy the model. But if DPO is stable enough, you could theoretically have a self-improvement loop where the model constantly refines its own implicit reward function in perpetuity.
It could potentially solve the super alignment problem. We don't need humans to label every single nuanced concept for an AI that's smarter than us. We just need to give it the initial goal of be more logically consistent. And then DPO provides a stable engine for it to lock in its own progress towards that goal.
The obvious risk, of course, is that the model's concept of logically consistent spirals off into some bizarre alien logic that is perfectly internally consistent, but completely incomprehensible or even dangerous to humans.
A risk I am willing to take for the sake of a good podcast segment.
Of course you are.
So that's recursive self-DPO, the potential engine of the singularity, powered by a simple binary cross-entropy loss.
It's a terrifyingly plausible extrapolation of where this could go.
Well, on that terrifyingly plausible note, I think it's time to wrap this deep dive up.
I think so.
To recap the big takeaway for everyone listening, direct preference optimization takes the incredibly complex, fragile Rube Goldberg machine of RLHF with all its pipelines, its multiple models, its PPO instability, and replaces it with a single, sleek, mathematically elegant equation.
It's one of those rare moments in machine learning where we actually seem to get a free lunch. We get better performance, more stability, and a vastly simpler implementation. It takes a hard reinforcement learning problem and turns it back into a straightforward supervised learning problem. That's a massive win for the entire field.
Been a massive win for anyone out there who wants to train and align these powerful models without having to sell a kidney to afford the GPUs.
Indeed.
Thank you so much for listening to this deep dive into DPO. If you want to read the paper yourself, and you really should, the math is beautiful. Check the bio for the link.
And don't forget to look at the appendices in the paper. The derivation of how the reward function maps to the optimal policy is really where all the magic happens.
Keep your tensors flowing and your gradients descending. We'll see you next time on Talk Tensors.